Hey everyone, this is Sina with another episode of Into the Bytecode. My guest today is Quintus Kilbourn, who's a researcher at Flashbots. And the topic of our conversation are trusted execution environments, or TEEs. So TEEs are a kind of secure hardware that allow programs to run with integrity and confidentiality guarantees. And they stand to have a big impact across a whole bunch of different areas, including how block building works in blockchains, but also how AI model training and inference is done. In this conversation, we talk about the history of TEEs, we talk about why they matter, talk about how they work, how they're actually architected under the hood, and we talk through a very thoughtful and first principles roadmap that Quintus and others have put together for making open source TEEs and secure hardware more broadly work in the world, and what we need to do on different dimensions to make that a reality. I hope you enjoy. So I thought maybe a good place to start would be just kind of hearing your own story of how you got involved in this mess to begin with. Like, how did you end up thinking about the problem of secure hardware, TEEs, maybe motivating where this came from in your story and the story of Flashbots, anything else that might be relevant background?
Sure. So I think maybe the best way of getting there is to start with the sort of the MEV Flashbots story. And Flashbots is, started as an MEV company. Phil, one of the founders, was the author of this like Flashboys 2.0 paper that really like sort of defined and pointed out this concept of MEV just as we were heading into the time when DeFi was picking up and MEV was becoming real. And one of the interesting things about MEV is that it exists in this like low latency space, but also it's all about information, all about privacy. It's about people, seeing what someone else is going to do, and you're trading ahead of them and making informed decisions based on that. And so, the tools we need to address these kinds of problems need to have privacy. They need to deal with this like very complex kind of compute that's involved in sort of optimizing MEV and dealing with like sort of this Turing complete blockchain environment we've created. And you need privacy. And, the tools we have today for privacy, outside of, the hardware side of things are quite slow and they have other limitations. And really like the only tool we're left with today to address these problems is TEEs and sort of other forms of attested execution. But we can just talk about TEEs as a broad concept. And so Flashbots has been really interested in this for years. And we have like, a bunch of people in the team who are like TE experts or have worked in this kind of stuff before. And part of that initial excitement was just saying, okay, here's how we can apply it to MEV. And we were thinking about that for a while. But as you're going through that process, you realize, whoa, these are pretty powerful primitives. There's probably some other stuff we can do with this. And then, people are ideating, and you'll see now that, this AI agent and TE thing has been really picking up on Twitter. But that concept is something we were thinking about like, a year or more ago. And as we were going through this process and realizing how valuable TEEs are and how they can still be useful in a world where software cryptography has caught up, and you have, even if you have lightning fast FHE and the optimal MPC schemes or whatever, you're still going to end up probably using hardware for some things. And so thinking through this, we think, okay, well, that's great. Like, why don't we just, this TEEs all the way down, it's going to be amazing. But then you stop and think, okay, well, we're in this, in this crypto world where we don't want to take on these trust assumptions. And like I think there's sort of two big critiques of TEEs, or maybe there are a couple more, but like two big ones that stand out in the context of the story. One is TEEs just don't have the same security guarantees as these like mathematically proven secure schemes. And, to that we have some responses. And I think the MEV case actually is a really good one because, the fallback, a broken TE, typically just looks like a public mempool, which is kind of the status quo today, or just trusting some central actor, I should rather say.
Right.
Like people trust block builders today or whatever. But the other critique is, in order to just even believe that TEEs are secure, like assuming they are implemented as you'd expect and they're robust against the attackers they claim to defend against, they still require you to trust that people with physical access to the machine are not going to, try break this thing. And people, the manufacturing supply chain from the designer through like TSMC or whoever, and all the different sort of intermediaries there, no one there's like, screwing with the hardware. And that obviously doesn't gel with this world where we're trying to minimize trust assumptions. And you can't really think of this TE as this is just like this magic piece of hardware that implements this security. There's some assumptions you make to believe that this thing is secure. And so really what I'm trying to do, what I'm looking at is saying, okay, well, if we do want to use this hardware primitive, how do we actually minimize the trust assumptions required to be able to rely on it in the long run?
I like that because you're kind of taking, a full life cycle ownership over the question of this being a trustless primitive in a similar way where sometimes we kind of think of blockchains as, okay, you put this thing inside a smart contract in a blockchain and that means it's decentralized and secure. But there's all these sorts of different questions, especially if it's on a layer 2, like where is its security deriving from? How distributed is the validator base? All these sorts of things. And you can kind of like peer underneath something like a statement that gives you this sense of security and confidence and realize that there's places underneath it where you can poke holes into it. And I feel like you're kind of doing the same thing with secure hardware.
Exactly. Yeah. Yeah. I think you can probably, there are some primitives where if you assume that you yourself are like a perfect auditor, you're not making any real trust assumptions apart from like mathematical hardness assumptions. You assume that, factoring is hard or something like that. Then you can, trust these ZK proofs that you're verifying yourself, etc. But for the vast majority of like secure primitives you're using, there is some assumption that some group of people is collectively not trying to screw you over, or some set of people are not colluding against you. And it's the same thing for secure hardware. And what we're trying to do is just like acknowledge that and try to make those assumptions as palatable as possible.
Yeah. So maybe before we go into all of that, like kind of zooming back out and taking this question of like, what is a TEE? Like if we take the platonic ideal of a trusted execution environment, what are we actually talking about? What properties does this thing have? And then I'm also curious to understand just how do these things work?
Right. So I guess that's a long answer. I'll take it in parts.
Yeah, go for it.
The Eli 5 explanation that I tend to give people is think of a TE as like your ideal trusted third party, with these assumptions in the background, assuming like Intel's on your side. And this trusted third party is embodied as like a little black box computer, and what it allows you to do is so someone sends some code to this black box, uploads some code to it, and inside of the black box it generates a public-private key pair and generates a certificate saying, this black box, I'm running this code with this code hash, and I've associated this public key with it. And then you can send the certificate to some remote party who looks at the certificate, verifies that this certificate is accurate, which is something we can get into, and then knows, okay, I now have this, this public key, so I have an encrypted channel through which I can communicate with this black box. And the black box is giving me all sorts of guarantees. It's guaranteeing that even those with physical access to it, this is the ideal case, can't see what data I'm sending to the program. It can't see it can't read like intermediate values from this program. It can't interfere with its execution apart from like just disconnecting the machine. And so really I have this like, perfect robot, trusted third party somewhere else, and I can remotely interact with it. And I never even have to like, see the machine to be able to interact with it. So that's kind of the idea. It's proving to someone far away that a machine is running a certain program. And that's, like the primary way to think about the value of that is like, it's a way for me to convince you that I'm going to do something, and I'm running a certain program, even though we aren't running any other kind of, interaction to give you any assurances of that.
Yeah. It's a really powerful primitive. Like it kind of rhymes with what one would imagine we'd have like with the end game cryptography. like when FHE and MPC and indistinguishability obfuscation and these sorts of things like come together, and you can have a program that receives private inputs, executes verifiably on them, puts the result back out. This is kind of what we're talking about, but just kind of like implemented in hardware with some additional trust assumptions that you're buying into.
Yeah, and I would say that so there's actually been some theory work, maybe just to give some context, there's been some theory work which has established, sort of looked at this question you're posing now, saying, okay, let's say we have this hardware, put aside the trust assumptions, how does that compare with these other privacy primitives? And really it's stronger than what you get with ZK and FHE and MPC and all these like buzzwords that we have put together, witness encryption. And the sort of additional interesting element that we get from TEs is this ability to make a program run only once, a signature only be, private key only be used once, or verifiably be deleted, or only run like n times. And this is something you'd get with like quantum cryptography only.
Right. This is like one-shot programs, one-shot signatures.
Exactly. Right. So like a basic example is there's a couple of use cases, but think of like a long-range attacks, like a long-range attack in a blockchain. You have a new user joining a blockchain. They're like following all the blocks, coming up to date with where the blockchain is now. But at every height, that validator set is signing blocks for signing a signature for the next block, in which the validator set might be slightly different. But if that old validator set who's long gone and no longer even part of the network still has access to those keys, they can sign a conflicting history, and a new user joining the chain isn't able to tell the difference. And so, like, I don't know if this is the most exciting use case, but this use case like illustrates the power of like verifiable deletion. If the only way you can get your stake out of the chain is by proving that you've deleted your private keys, then you protect people. You protect against people signing, like doing these long range attacks, for example.
That's super interesting. What are, maybe before we get into the architecture and the trust assumptions and stuff, so what are, if we have a primitive like this, like again, taking the Platonic ideal of it, once we figure out all of the details, where do you see this being used?
So I think the extreme example here is to say, okay, we 100% back this thing. We just like, this is a T given by God. Then one of the interesting things that you can look at is quantum money. So when, the quantum people, I don't know if it's Scott Aronson, I don't remember exactly, came up with quantum, they came up with this idea of like a one-shot signature. You have your quantum private key, and if you see a signature from this quantum private key, there can be nothing else signed with this private key because the entropy is collapsed and this private key can only be used once. And what you can do with a scheme like this is you can basically have a digital currency that doesn't rely on a public ledger. Because like the reason we need this public ledger is we just use a cryptography to verify that someone has ownership. But the other thing we need protection against double spends. And that's why you need the public ledger. But if you have private keys that can only sign something once, you can prevent double spends because no one can sign two conflicting transactions. And so if I want to transfer you some coins, I sign the coin. So I have a certificate from the previous person who sent me the coin, which is just a chain of signatures with quantum keys. I sign this chain, adding your public key to the end of this chain with my quantum private key and send that to you. And now with this certificate, you can prove that I no longer have custody of this key, of this coin, and that I have transferred it to you. And so based on this, you can do more complex stuff. You can have like a blockchain-less digital currency. And Ts obviously are much more programmable than this, right? Now, there are some schemes to like build more complex stuff on quantum. But, you wouldn't need like one certificate for one coin. Maybe you have like one certificate for many coins, a variable number of coins. And what's exciting really, I think, is, for low value use cases, even today, maybe it makes sense because, posting to a blockchain is expensive. So if you have like some low value transaction in between us, we just sort of, we trust that, this $10 transaction probably isn't going to be double spent by someone who's like broken their TE. and then every 30 minutes or every at some time interval you post to some blockchain to protect you against double spend that could have happened if someone did break their TEE. And that's kind of the same logic that rollups use today anyway.
So the TEE in this case is like basically a computer that's keeping track of the user's state or unspent transactions, and kind of like enforcing the fact that they can't like say two different things to two different people.
Yeah.
Because this is a computer running like a verifiable program that everyone knows is executing correctly. So their counterparts can basically take the TEE's attestation and kind of know that this is the case.
Yes, exactly. And the buzzword to look at here is encumbrance. So we've encumbered these private keys, and the encumbrance implies this additional layer of logic which prevents even the owner of the public key of the private keys from using them outside of the bounds of what's allowed. And the TE allows other people to be convinced that this sort of a limitation on how the private keys can be used is being applied.
Yeah. So I've also kind of heard you talk about how TEEs are being used or could be used for in AI for model training, training on private data or inference in a verifiable way. Can you sketch out like what's going on over there?
Yeah, so I should, give a caveat that I'm not, the AI guy, but from afar, it seems like there's a couple of things happening. So the primary reason we're seeing this conversation with TE and AI, in the same sentence, is that TEs provide us assurances with high performance, like I was saying earlier. And, like these AI models are huge, inference is expensive, and we want to, serve millions of queries a second. I don't know what the requirements are, but you just can't do this with FHE or whatever's available. And by the way, you've had like OpenAI and Apple and all of these companies make public statements and moves to use hardware security to facilitate AI stuff. It's not just, the crypto bros getting excited and hopping on the wave. And so some of the things that people are interested in is like, okay, here's a basic example. You have an AI model. I can't run it on the edge, or you won't let me even run it on my side because you don't want me to steal the weights. So I'm going to send you my query, but I don't want you to know what my query is. And so if you can prove to me that your model is running in some secure hardware, then that gives me some assurances that you're not, using my query, you're not storing it, or you're only training the model on it in some like differentially private way or whatever. And similarly, if we have these marketplaces where like there's this idea that, you have specialized models for handling certain tasks, and then some market that like takes a query and routes it to the optimal model based on some pricing or whatever. And for that market to exist, you need to know that when your query gets routed to the fancy model and you're paying the premium for it, that your response is actually being handled by the fancy model. So, TEs provide you a way of knowing this as well. But I think the most exciting or like interesting use case that we've seen probably on crypto Twitter in the last week, couple of weeks or so, is these like verifiably autonomous TE agents and Shin and Andrew from Flashbots. Sexy Sun is Shin's handle on Twitter.
This is kind of the same. This is kind of the same problem, right? Except like of like having a model inside a TE run inference. Except that model basically has persistent memory and its own identity that it's living into.
Yeah,
but maybe you should describe what we're talking about first.
Yeah, right. So basically, like what they're building is a TE, this like system running on TEs, which is basically an AI agent implemented, with an LLM or whatever, that's given access and exclusive access to a Twitter account and like an ETH address, or you can add whatever you want there, but those are some examples, some like digital credentials, and because the account is generated or like the password is changed from within the TE, and the private key is generated from within the TE, if like verifying this attestation that as long as the TE hasn't been breached, that this LLM is the only agent with access to these funds or with access to this Twitter account. And in some sense, it's like this LLM has been set free. And they've been playing it quite safe. I don't know what the current experiment they're running is, but the initial experiment, they said, okay, 7 days, we're only going to allow this model to transfer and receive ETH, and we're starting with a zero balance, because you never know where this is going to go. But I think this is like super super exciting, and I think it unlocks a bunch of stuff. But yeah, maybe let me not get too excited. Yeah,
totally. Yeah, I guess the kind of the things. Yeah, so we basically get this autonomous piece of software that can have access. I mean, the thing that's also different with TEEs and with, other cryptographic mechanisms is that a TEE is like literally a server. So it can be connected to the internet. It can make API calls. It can, curl a web browser and read what's on Twitter and like post a response. I think that the thing, which I'm sure this is like the beginning of a science fiction book, but like this is still one server that we're talking about, right? So the human still has the ability to unplug this server, but the next step will be that it's replicated across multiple servers, and then we're screwed.
Right, and you have all of these, not all of these. There are a couple of companies that are pursuing this idea of a decentralized compute cloud, right? And then as long as you make the on-chain payment, you're guaranteed to have access to some GPU until your credits are used up or whatever. And then you can imagine these agents, whatever, like trading on-chain or doing whatever to make money, and then using that to make a crypto payment to pay for their own like compute bills, which is, exciting and scary and everything at the same time. But the key point there is like, it's not that hard, not that far away.
Totally.
Yeah. And I think that one of the biggest critiques of these kind of systems is, but the security assumptions are not that strong. And I guess there's like an asymmetry to it where, like, yes, if you're the one relying on the system, the security assumptions being strong is very important. Like if my private keys are secured by some system, I want the assumptions to be not that strong and quite palatable. But if you're on the other side of it, and some guy's running an AI in a TEE, the assumptions may not be that strong, but I can't, I'm not going to go, I don't know how to break it. It's hard, and so for the majority of us, that critique is like, it's valid. I don't want to maybe rely on this agent too heavily, but I also can't stop it. You have to convince a very sophisticated agent to try stop this thing.
Yeah. And I feel like for cases where, there is more of a need for security, like let's say I'm, that the query that I'm sending to the model includes a bunch of very private personal information. Like it's like a bunch of pages out of my personal notepad, and it includes, private data. Even in those cases, you could, like, the TE software could be programmed such that, for instance, it keeps no logs, right? Like you could design it that even if it's broken into, you can kind of like put bounds around how much leakage there would be. Yeah.
So, okay. Very good point. So basically, there's like levels of thinking about like hardening TEs. What I've been working on the last couple of months, and which we'll speak about later, is sort of the real like base level. Like, can we just make this TE hard to break? But then there's this layer on top of it. Like, okay, assuming the TE will get broken, how do we mitigate, or how do we sort of ameliorate the situation? Reduce the impact of a break. And there's all sorts of ideas here. One is forward secrecy, which is this idea that you basically, I guess there's different ways of implementing it with like rotating keys and these kind of things. We can like rotate the private key, but the public key stays constant. And so the user doesn't suffer UX issues, but the like encrypted data is encrypted by a different key. And so if someone breaks the TE and gets a private key, they don't know, they can't decrypt the data from things before the rotation, right? But not storing logs is like a sort of a kind of a different way of getting there. Although maybe with weaker assurances. Other approaches in this direction say, like, look, many of the attacks that people carry out in TEs, or some of the easier attacks, involve extracting like a couple of bits. They extract some like access patterns or whatever. And if we're in the MEV use case, someone extracting like 1 bit per second or something isn't really a concern, because 12 seconds later, we've already processed the data. It's on chain. It's fine. Or we're processing so much data, like leaking 1 or 2 bits is not that big of a deal. But then obviously if someone does leak like a critical private key, that is a big deal. So there's like some nuance to it. And for different applications, you can have like different arguments for sort of the gravity of certain kinds of failures.
Mm-hmm. Mm-hmm. Okay, well, maybe let's get into some of the trust assumptions. Maybe a first question before we get into that is, how do these things actually work? Like how do you have a trusted enclave in hardware in a way that can't be broken into?
Right. So the different TEEs will have different assurances. I think the key part to understand here is the remote attestation flow. So let's take an example of SGX or TDX, which are manufactured by Intel. The chip is this chip that is supposed to be used to run this TDX module or whatever later is built by Intel. In that process, they burn a key into the hardware. In this case, into like an eFuse, and they keep a record of the public key that corresponds to that private key.
What's an eFuse?
It doesn't matter. It's some non-volatile way of storing
bits in hardware.
Yeah. And like different there are alternatives to that, so I don't think we have to fixate on that too much. And then this gets the chip gets sold to some cloud vendor, skipping a bunch of steps, obviously. And now during the boot process, the chip will check, okay, is the like expected firmware running? This firmware will control some of the important logic for the TE later. And if everything looks good and we have the right firmware and the right like low-level software, then this hardware key will be used to sign this like low-level software saying, okay, this is actually what's cracking, and this is what's running. And so Intel can then receive this signature saying, okay, look, with this device, we made it, we checked it, it's like built according to specification, and it's, assuming no one has gotten the key out of it, then it must be running the right firmware, and then they can issue the certificate saying to other people, like, okay, this is good hardware, this is what we expect it to be. And then you can you can use that to bootstrap a program. So now in that sort of initial process in which the hardware key is used to sign the low-level firmware, you can also generate this public key, public-private key pair, and then that private key, which the chip holds, can be used to sign some additional programs. Like, okay, yes, I'm running the low-level software that's like helping to isolate these programs, and now I'm running a program in this like special trust way. Let me sign a certificate saying that I am doing this. And so the end user can receive this like chain of signature saying, okay, well, I have the signature over this code hash saying that this firmware is running on this chip, and then I know that this firmware is running this expected application. So tracing it all the way back, as long as I trust Intel and I trust that no one has like broken this chip, then the expected hardware should be running this application. And then the hardware is designed in a way that we isolate this program. And there's like the primary threat model that SGX and TDX and many of these Ts tries to address is other untrusted code, right? So because they're in this cloud setting and thinking about a multi-tenant world, they assume that there's like, okay, we have this application's what we want to give assurances over, but also running on this machine, we have this untrusted operating system or hypervisor and other VMs, and we do not trust those at all, and that we assume they're trying to steal the data. How do we keep those separate? And that's kind of what a lot of the assurances, that's what most of the security focus goes to.
So maybe retracing that in simpler words is, there's this initial private key that's burned into the hardware, And when this chip makes its way to the cloud provider or to some, user somewhere in the world and is booted up for the first time, this private key, there's some very low level firmware process that boots up, and somehow internally between the firmware and that initial private key, somehow there's a check that this is the correct firmware that's running. How does that happen?
Yeah. Well, boot processes do this anyway. I don't know the intricacies of this part of the process very well, but many
this is one of those problems that if we want to peer into it, we'd have to like open up the rest of like the body of human knowledge, like down to like how silicon is made from sand and like how the galaxies were formed and stuff. You got to draw the boundary somewhere in like what we can talk about and abstract the rest of it away.
Yeah, for sure. But I mean, just to put this in context, like this isn't something like generating a certificate and signing that, yes, and maybe generating this like public-private key pair. That is something that's like more specific for attested computation and like TEs. But the idea that the hardware checks what low-level software is running on it, that's not like specific to TEs.
That's something that happens all the time.
Secure boot processes and these kind of things also check, okay, like what is the hash of the code that is running in the machine right now? Does that match what I'm expecting? Oh, no, it doesn't. Okay, someone must have uploaded some malicious firmware or whatever.
Yeah. Right. That makes sense. And then as soon as this firmware is kind of, certified by the manufacturer, then this firmware, then you kind of like get this chain of trust, and the firmware can attest that other, higher level pieces of software that's running is also attested to.
Right. Yes.
Okay. So now we basically have a certificate from Intel that a piece of software, which is the software that's managing the enclave, is the correct one. Is like the one that Intel had intended to put into this chip.
Right. Yes. And also that the chip which is running this low level firmware is the chip which we expect it to be. It is this, it has this x86 instruction set architecture, and it does, execute code in the way that you expect it to be. And therefore the like low level code that's running on top of that, the like SGX module or whatever, or TDX module, that is also executing correctly because of the correctness of the hardware.
Right. Okay, so then now we're kind of executing this higher level code, and you were talking about most of the work has gone into making sure that other software that's running on the same device can't kind of impose on it. How does that work?
I think I can give you some insight into this. Again, not like the expert on this. The true answer is that for the most important point here, I think is for most TE, but actually all of them, we don't know. That piece of code is
closed source. It's
closed source, and we're trusting Intel or AMD or whoever.
Yeah.
In the vast majority of cases anyway. But the idea here is that, like, look, we have some special CPU mode, and that handles these specific enclaves, and so they'll do some things like encrypt when this code running in the enclave, this protected code, trusted code is the term they use, is running in the enclave, or we encrypt everything that goes to memory. So there's no unencrypted data in memory, and we have strict permissions that prevent the operating system or untrusted hypervisor or whatever from accessing this part of the memory. And they might clear caches in between switching between different enclaves. And here you get a lot of diversity because there are different ways to implement the TEE. And you have academic proposals for how to do this, and you have actual industry stuff. The most interesting way of segmenting this that I've come across was from a paper whose name I forgot, where they talk about like temporal and spatial separation. So spatial separation is like, okay, we're only going to allocate some part of the cache to this program and no other program or process or whatever can use as part of the cache. And so it's spatially separating the trusted and untrusted code. But the problem is that this then slows down, like takes away from your performance. And then you have like temporal separation, which is okay. We have a processing unit, a CPU, and when we're running the trusted code, we're not going to allow it to switch to the untrusted code, or you're going to run it for some time period and then like take turns using it as opposed to like more rapidly switching between them.
Right.
Yeah, and there's a lot of details, and I feel like I'll probably misspeak if I try go into them too much.
It's all good. Yeah, we can consider this more of like an impressionistic sketch of what's going on rather than like a true to all the details. It's like a super, seems like a super fun problem to work on. Like you're basically designing this computer that is running inside an adversarial environment. And so you're like constantly thinking about what resources others might have access to and like provisioning them and unprovisioning them. And it seems like a really kind of interesting technical problem to work on.
Yeah, I think what you'll hear a lot of skeptics say is say it is very interesting, it is very complicated, and because it is complicated, it is like doomed not to succeed. Like it's an old adage, like you don't add security, you remove insecurity, and because people are trying, Intel and AMD are trying to achieve like really high performance without adding a lot of additional hardware. They are taking on this like very complex challenge of running untrusted and trusted code together, and that's why you have seen many exploits over the last couple of years. If we just did hardware isolation and said, okay, the trusted code is the only thing running on this processor and there's no other interference, then that's a much simpler approach, and that's what people advocate for. But that's not the architecture that
so why aren't these firms doing that?
I think it's sort of hard to speculate. I think the sort of answer that has made the most sense to me is that it is more expensive to have this additional hardware, and it is going to be lower performance. And so, the sort of like the caricature of the use cases that were relying on Ts before, and the Ts were created for like GDPR use cases. So it's some guy trying to get a regulatory check saying, hey, I'm receiving my medical client data and I'm running in a TE, and it's like it is a little bit hard for AWS to snoop on it, and it's a little bit hard for some hacker to get it, and that's good, and you get the check, and now you can like legally operate. I think that's the justification. Maybe someone will angrily tweet at me on Twitter if not, but I actually hope that's the case, because I haven't yet heard a good justification. And I should say that we're talking about TEs here, but there are other forms of remotely attested execution, like Ledger, like the hardware wallet, also can do remote attestation, and they have this isolated kind of design that I was talking about. They don't run trusted and untrusted code together, as far as I can tell. And the reason they have remote attestation, the primary reason, is because they are worried about supply chain attacks. So could you imagine that you order a ledger, some smart guy at the delivery facility sees someone ordered a ledger, swaps it out with their little modified ledger. You plug it in, upload some private keys, you think it's safe, but actually it's not. Your private keys are being sent off to this other attacker who steals your funds. And so because they know which public keys correspond to their ledgers, when you power up your ledger, you plug it in, it does an attestation, and they give you a thumbs up saying, okay, this looks good to us. This is actually a ledger that we manufactured. And so that is more secure. And they also have ledgers are obviously also built to resist physical attackers to some degree, or to a relatively high degree. But they just have nothing like the performance like SGX or TDX.
Mm-hmm. Mm-hmm. Yeah, the user interface is also 2 thumbs typing, so it doesn't need very high throughput. I'm a
4-finger guy on the ledger.
Really?
Because it has the buttons on top, right? So
right.
Maybe I'm.
Yeah.
Maybe
I think you're right.
maybe it's poor OPSEC. I just like leaked that I'm using a Ledger Nano. That'll come after me at some point.
Right. I feel like half of everyone working in crypto is using the same device, so you probably didn't leak that much information. So you've had these two really great blog posts recently, and in there you're kind of describing how at a high level there are three threat vectors that one needs to consider when thinking about secure hardware. The first one is what you say is a remote software adversary, which is basically what we're talking about, right? Like other software running on the same chip.
Yes.
The second threat vector is a physical adversary, which is basically someone who has access to the chip, like the cloud provider, AWS, where this thing is running. And then the third threat vector is a supply chain adversary, which is like somewhere in this process, from the chip being manufactured to transported to boot it up, like someone tinkers with it in some way.
Right. Or even the original design was, designed to undermine your security, but then advertised as something else. So either a supply chain actor or like the initial designer of the hardware.
Yeah. So maybe talking about the second point before we get to the supply chain one. So the physical. So, and maybe thinking about this case of, there's an interesting distinction between, where we're talking about the model training and inference use case where OpenAI or Apple have their private clouds, right? That's a case where the TE is running within a cloud that's internal to a company, so they can be much more careful about who has access to these servers and kind of like gate those in more precise ways. Whereas when we're talking about like a open distributed protocol allowing you to deploy these things, then this TE could be running on any machine anywhere in the world. So how does the physical environment impact what's possible?
Okay, so I think maybe just one thing to add there is that you could, in theory, create this like more open design and then require it to be only run in some cloud environments, and you'll only interact with this thing if it's also signed by AWS. That's not at all what we're aiming for, but it's a possibility. I just want to put that out there to add some nuance.
Right, the two aren't mutually exclusive. Like, let's say in the case of Flashbots' new kind of builder net architecture, you could say that, okay, this is an open distributed network, but like the servers have to be housed within these cloud providers. That would be a way to simplify the trust assumption. But you also don't necessarily need to do that.
Yeah, the ideal case, is like the most decentralized case, in that it doesn't matter where someone is running this, and there are like 15 different manufacturers who could produce it. We don't rely on only one, and then a bunch of different designs, and we sort of have all of these coexisting. And so if one manufacturer stops producing them, it's fine. We don't rely on cloud providers, and it's like, very, very, there are very few sort of central choke points in the system. And I think, going through this whole conversation, we can always talk about the ideal case and what we're striving for, and what like every hardware security person I've met will react with that is like, no, it's too hard, or you can't do it. And I think that's fine. I think there's not every hardware security person, but many. And like, really, I think there's a need for us to stipulate this ideal, what we're going after, and then to look at milestones along the road and say, okay, yes, that is very hard to believe we can do, but we can get closer to it with these milestones. And look, we actually can get there. And so, to your question about physical security, typically when hardware people talk about the security of the tamper resistance of a device, they'll talk about cost of attack, because the assumption is that no matter what you do, for a big enough price tag, someone is going to be able to break this thing. And there are there are attempts to make things more formal and more mathematical. So if you look at like side channel attacks, which are basically people through a variety of means, trying to extract data about a computation just by listening to the chip passively, or like you're probing a certain number of wires to see what the what the 1 or 0 is you're getting for this computation. And there are sort of mathematically proven approaches to dealing with these. And so the main way of thinking about hardware security is like cost of attack. But then there are these approaches to gradually make the security assumptions more and more formal and mathematical. But just like in software cryptography or mathematical cryptography, at the end of the day, you're assuming without mathematical guarantee that something is true, that factoring is hard, or whatever, assumption you're making for your cryptography to hold. In the hardware case, we also ultimately going to have to make this assumption, and I can talk about where we'll probably have to make this assumption, or some places we know we'll have to.
It's at bottom going to be like a statistical assumption or something like that.
You're going to assume that something is physically hard to do.
Yeah.
And I'll give you an example of that in a second, but I just want to give a bit more context there. Like in the hardware world, the idea of security through obscurity is prevalent. The common criteria, which is the way that secure hardware is typically evaluated, actually explicitly rewards designs where implementations where the design is not publicly available. Because in reality, it is kind of true that it is, if for an attacker who knows nothing about a chip, an attacker who knows something about a chip and it's the same chip, and they're probably going to find it easier to attack the chip that is where they have some information about the design. But the counter argument is Linus's law, which says, all bugs are shallow given enough eyes. Yeah. And so the idea is look, if we actually could get some open design, we could start building more confidence in these assumptions. And we say this thing is hard to attack. Well, let's make it as easy as possible for attackers to attack it, leaving only the necessary assumptions and see if it holds. And so that's kind of one of the directions that we're pushing in, and there's some academic groups who are trying to do this, and I'm just very excited about their work.
Into the Bytecode is sponsored by Splits. Are you tired of sacrificing security for usability? Splits believes it's still way too hard for teams to self-custody their on-chain assets. They're building a new kind of internet-native bank on top of Ethereum. Splits makes it easy for teams to manage the whole lifecycle of their finances, from structuring revenue-sharing agreements, using payment flows like splits and waterfalls, to managing those earnings once you receive them, using passkeys and smart accounts. Splits is being used by teams like Protocol Guild, Zora, Songcamp, and others. I'm a big believer in them and recommend checking them out. You can learn more at splits.org. Yeah, so what does the physical security look like? What would an attacker do? What do defenses against those attacks look like?
So I guess so the easy attacks, right, which current TEs are vulnerable against, is some guy going and basically sitting on the wire between the CPU and RAM. And yes, okay, the things that are being written to memory and retrieved from memory are encrypted, but they're not always integrity checked. And so I could replace, what is written at memory location A now with what was written there, 20 seconds ago, and do these kind of replay attacks. And because the processor is only checking that the encryption was correct and decrypting it, you can fool it and make it think that, the value is what it was 10 seconds ago and not the updated value. But these are actually really attacks that we can address. They have been addressed in other architectures. These are the really easy ones. The harder attacks are side channel. Side channel is also a bit of a broad category, but side channel attacks and direct readout attacks. And so side channels just refer to people extracting data from there's some nuance to it, but basically people learning about the execution of a program, not because they see the input or the output, but because they see something about the intermediate computation. And so like timing channels are a good example of this. And if you write a program that like, says if my private key starts with 1, loop forever, and if it starts with 0, just like return, you're gonna leak some private bits, right? So there's some expectation for the application developer, but leaving that aside, we look a bit lower, saying, okay, let's say you're using the same number of instructions for every path the program is running or whatever. There are still some ways that attackers can extract information from your program. So some of the like harder ones are like power analysis, where the attacker will monitor how much power is being used throughout the computation, and from that they're able to extract some information about what's happening. And it's much easier if they know what application is running, but that typically is the case when you have remote attestation. And so and this is where I was talking about this mathematical guarantees. Like there's this work on private circuits, hardware private circuits. I think like HPC3 is the sort of cutting edge there. I don't want to claim that I am an expert on that, but there they have some mathematical guarantees where they say, okay, well, as long as the attacker can only probe D wires and cause like K faults, which is like they cause a bit flip basically, then you still have secure computation. And then they prove some like equivalences between this like deprobe model and a statistical model where the adversary is learning like with probability epsilon something about the value of every wire. And so they get really like formal about it. So that's the side channel side of things, and you need to defend against that. And part of the challenge there is that like, okay, we do know ways to mitigate these side channels, but when we do that, we have to pay for that. We have to pay for it in like having a bigger chip. We have to pay for it in being slower. We have to pay for it in maybe like needing to use more random bits, which can also affect performance. And so that's the side channel stuff. And then you have this like direct readout, like invasive attack kind of stuff, where someone is like shaving down the chip and or like trying to like directly read out some values and registers and whatnot. And for that, so the concept I was going to talk about earlier in terms of like backing trust assumptions is this idea of like tamper evidence and the most
cool.
So the most interesting instance in which tamper evidence is used is puffs. So it's like this physical unclonable function where
PUF,
yeah. So the idea is, look, in the manufacturing process, there is some natural variation. Even if TSMC with the EUV machines, like these highly sophisticated machines, even if they wanted to, they couldn't precisely recreate the same chip every time. There's going to be like very small variations, and so like gates are going to take a slightly different time to fire. And typically, these variations are not that impactful, but we can expressly design the chip so that these variations get amplified. And then we can make it really sensitive. This is where the tamper evidence comes in. So that if someone tries to like actually physically go into the chip and see what's going on, they disturb the electric properties of the chip so that the puff response, so that the electrical properties of the chip change. And if we are able to use these electrical properties of the chip as a private key, or as the secret used to see the private key, then we have this cool property where, okay, the manufacturer produces this chip. The private key only exists, the secret only exists once the chip has been manufactured. And so they don't have to promise that they're deleting a copy of it. And now this key lives in the chip. And in order to get access to it, the hope is that someone will have to physically go in. But as soon as they physically go into the chip, they disturb the private key and they destroy it.
They change the private key, yeah.
And so this is like the kernel that this is where the hardware key would come from. And it's like a very essential part of this idea of like a...
That's like the root of the whole trust, the chain of trust.
Exactly, right. But this tamper evidence property is useful for protecting this private key, but it's also useful for other kinds of defenses, like direct readout attacks. If someone is like physically attacking the chip, and maybe they're not going after this key, but they're trying to do something else. And if we can have the puff be sensitive enough, or some tamper evident mesh which clears, like, zeroizes RAM if it's disturbed. If we can make that sensitive enough, then we're defending against physical attackers. Obviously, easier said than done. But this also, it sounds like magic, and it kind of is, magic. But like cryptography also sounds like magic, and actually, the concept of puffs has been around for a long time. And so you have a lot of papers which will show that show some attacks on puffs, but typically those are on strong puffs, which is they're trying to do something much more complicated than this like private key generation concept that I was talking about. And so they're all like, if I'm not mistaken, typically in like what you see in your the little microchip on your credit card, that will have a puff in it. So it's not a immature technology.
Such a cool direction of work. So what has been motivating this work so far? Like before it became relevant to our blockchain use case, like why are people looking into this stuff? Like you mentioned the GDPR thing. I guess you're saying the credit card chips are using some of this technology, but like what's the scale of like attention and resources that have gone into this problem so far? And do you expect that to kind of like inflect now in similar ways that, say, some cryptography stuff like ZK kind of like went through with blockchains? Or how do you think about that?
So the answer is like yes and no. People have been paying attention to this for a long time. Yes, in the sense that, secure hardware, the chip on your credit card, the hardware that underlies your ledger, these kind of things, that all has, received a lot of attention over the last couple of years. And so over, the last couple of decades. And so there is a lot of research into, building secure puffs and doing this sort of side channel resistant chip design, etc. But the emphasis has been kind of different, and a lot of the side channel stuff is quite recent, actually, in the last 4 years or so. But a lot of that research, but there has been this cat and mouse game where someone will come up with some hardware and they say it's secure, and then it gets broken. Someone presents it a black hat, and then these guys go again and they make it more secure. And there's a whole bunch of techniques people use. They put cameras in there so that if someone, decapsulates the chip, some light comes in and then it sterilizes everything, or some acid vials which are easy to disturb and it breaks the chip, etc. But yeah, it's crazy. If you're really bored on not even that bored, if you're interested for a weird Sunday afternoon, get a cup of coffee.
We know how Quintus spends his weekends.
and then look at the patents for tamper-proof hardware, and you'll find the stuff where people have different washers with a screw that runs through them, but they're different sizes. And so if someone undoes the screw and screws it back in, because the washers are different sizes, they won't be in the same position. And then you make them transparent, and then you have a sensor on the other side that detects light shining through these washers. And because they've moved, the light going through looks different, and therefore, now someone's tampered with it, and the chip stops working, or some crazy stuff like that. But that's not what I'm advocating for. I just thought I'd mention it because it's interesting. So have people been working on this? Yes, for many of these problems, but no, in the sense that the emphasis has been very different from what we care about. What we care about is being able to assure this end user that the hardware they're interacting with, perhaps remotely, is indeed secure, without them having to take on board a bunch of trust assumptions, or as few trust assumptions as possible. And the traditional hardware world has been focused on hey, we're going to make this thing as secure as possible, and we'll get the certification, and we'll just sell it. As long as someone's buying it, we're happy. We don't want to draw too much attention to ourselves by maybe opening this up and getting people to break it. And the other guy who's buying this hardware is great, this guy's telling me it's secure. too easy to break, I'll sue him. And that is maybe fine for that setting, but we don't want to exist in a world where, oh, okay, my secure scheme broke, let me sue someone. That's like sort of the exact. We don't want to rely on this legal apparatus anymore, and so you don't have any real open source puff designs, for example, which is really this like low level assumption of physical hardness that we need to be testing. And so there's a really cool group in Belgium at UC Louvain, the university there, that's like trying to do this kind of stuff. Similarly, I will say that most of the secure computation stuff has been targeted at like the ledger kind of use case where you're just signing things. And now we're talking about this, this crazy world where not only are you're not just running AES, you're running like an arbitrary application in there. You're running an LLM. That's from right. Someone who's been like trying complex. These guys have spent their hours, days trying to minimize the logic they're running in this little small secure enclave, so that there's like so little they have to audit. The trust compute base is so small, and here we're like, well, just put it all in there. Just put an operating system; it'll be good. And so there are very big differences as well.
Like the transition from Bitcoin to Ethereum, right? Of like, now we have a Turing complete computer.
Yeah. Maybe there's probably a DAO hack in the path to success, but Ethereum survived, so hopefully we will as well.
Right. So these things have been around because it makes me think like talking about secure hardware begs the question of like, what about all the rest of hardware? Like, what have we been doing so far to this point? But I guess what you're saying is when I have a MacBook and I boot it up, it does some version of what we're talking about, but one, the stakes are much lower, and I'm kind of implicitly trusting Apple with a whole bunch of things. And then Apple also gets to say that I bought these chips. I guess now they're manufacturing their own, but they can say that I bought these from these other firms and they made me these legal promises, and I can sue them if something breaks. So I can kind of like pass the buck to them.
Yeah. So that legal point is a big point, but just to set the context, maybe with a little bit of doomerist, embellishment. We've been talking about TEEs, and I think TEEs are really interesting because they're a positive case to say, okay, if we have secure hardware, we can do more than we can do today. But if you just want to be a bit more like cynical and you look at the world we have and you say, what are the trust assumptions actually implying for us? Well, okay, your phone, your car, your planes that keep you in the sky, all of this is running on hardware, and you are just assuming that whoever manufactured this hardware, or the many actors involved in manufacturing it, actually did implement the like tamper resistance guarantees that they wanted to, and also did actually not implant a backdoor that can completely undermine the system and send all the Teslas off the road at the same time or whatever. And obviously there are defenses against this, and like implanting a backdoor in the hardware is a hard thing to do, but I don't think it's something we really take for granted. And there has been some focus on this in the like Web 2 world, or like the traditional hardware world, because where they say, okay, well, Intel goes, okay, well, we're going to outsource some part of our manufacturing process to this vendor in China or Taiwan or whatever, and we don't trust them, and so we're going to do a bunch of things like encrypting our logic and whatever, so that they can't toy with us. But the end user is still just trusting Intel. And so like if you look at Ledger, like Ledger has all of the incentive in the world to like let the end user verify that they are providing them with very secure hardware that doesn't have a backdoor. But because of the way this like traditional world works, actually the hardware design and even some of the low-level firmware is closed source. And so even for these very critical things, we have to make these trust assumptions. And like my dream, and I think for many other people's dreams, like we use this like positive use case of trust minimized TEEs to break through and like show the world that you can do something with trustless hardware, and that there's value in minimizing these trust assumptions, and then ideally causing a bit of a cascade and moving a lot of the other hardware that we're all making trust assumptions in to a safer setting.
Yeah, it feels like the sort of a thing that just none of us have been aware of. I mean, I can't even say that I've thought about the fact that when I'm on a plane, the hardware has all these trust assumptions. It's just kind of been invisible in the background. But I do feel like, I mean, it's interesting to think about, especially in this world, and considering that a lot of these chips are manufactured in Taiwan, right? And do you see outside of our kind of crypto lens on this problem, do you see any other kind of like macro forces in the world that are playing into how the broader field of secure hardware will evolve?
Yes, for sure. I think there are some specific instances where countries are very, forward on their they have a very digitally forward, digitally minded policy. They want to, move they have like digital. Well, I guess every country has some digital database for their citizens, but they want to put it in some secure location and these kinds of things. And I guess they also don't want to make these trust assumptions. And it's a bit different, the citizens are supposed to trust the government. Maybe in different countries, people trust the government more or less. But it does get to the point where if your passport has a ID chip in it, has a little secure element in it, or Java card. Actually, I think those terms are used interchangeably. And that's manufactured by someone as well. So I think there are like geopolitical reasons to be interested in this. And certainly if you're giving people assurances based on around AI models, which have become so geopolitically hot, you probably also want that to be, to have those assurances be like somewhat neutral. If it's like America saying, "Oh, look, like Intel made this, and so it's good." I don't know if China's going to buy that necessarily. And you do have historical examples of the NSA implanting hardware backdoors. So it's like it's not crazy. It's not like a tin hat theory to go, oh wow, what hardware, like all this hardware is like, we're making all these trust assumptions. Like there's obviously a level to which you have to be reasonable. Like I don't manually go inspect my car when I buy it to make sure that all oil pipes and things are well connected. But at the same time, there are plenty of examples of the last 10, 20 years of hardware Trojans being found out in the wild. And that kind of begs the question, do we see more hardware? Like, are there hardware Trojans in this room right now?
Right.
Perhaps. I don't know. And
well, it feels like a relatively straightforward attack vector, just given the market structure and the fact that there's like a couple of players that you need to go have, that are operating under your jurisdiction, and you can just get them to do something.
Yeah, I think the counterpoint here is like, say, yes, hardware attack vectors, hardware backdoors are a technically feasible approach, and we have examples of it happening in the past. But look, they're hard to pull off. There are only a limited number of actors who can do it, who are involved in this supply chain. And typically these guys run trillion-dollar businesses, and they have a reason not to want to screw it up. The real attack concerns is the user fat fingering something, or your software implementation not being secure. And then underneath that, okay, someone like physically attacking your hardware, and only, the last kernel is this hardware backdoor. And I think there is some truth to that. But my counterpoint is like, one, okay, yes, we've seen this stuff happening, but also it feels kind of like you do want to minimize your trust assumptions, and you should maybe address these like harder things first. But if you can't convince yourself that you can change the foundation and make that more secure, then it feels a little bit, it's much less motivating to like work on the stack, because it's ultimately a limit to what you can do. And that article that you were referencing that I put out makes this argument saying, look, we actually do have the technology we need, or like there's enough active research in addressing these sub problems to be able to get to this point where we do have these like very low trust assumptions in the hardware. And really knowing that, it makes no sense for us to ignore it. It makes no sense for us to say, oh, we'll start worrying about that when this like cyber war moves to the hardware world and we can't trust our iPhone anymore. It's like much better to start working on it now.
Yeah. Well, and I feel like the kind of like crypto context of just like having a decentralized builder network is like the perfect forcing function on this problem, because it puts value directly at stake, and that's what we need to start making progress at a faster rate.
Yeah, we're being attacked by North Korea. It's like it is a nation state level threat model.
Right. Well, okay, so I guess we've been wading our way into the third threat vector, which is the supply chain. But I feel like it's worth talking through this, especially because it's the topic of the second whole piece that you wrote, and it was fascinating. So you've kind of talked about it a little bit, of how this the private key is burnt into the hardware with this eFuse thing, and there's a series of handoffs before this thing is deployed in a cloud provider. But what does this supply chain look like, and how do you think about where the threat vectors are and what can be done here?
So let me, you can break the problem down into like some smaller sub-problems. So, okay, we've spoken already about this problem that we don't want the key to be injected. We don't want the manufacturer, Intel, TSMC, whoever, to like on their laptop, generate the private keys and then like inject it and then promise to delete it. Okay, so we have puffs and we have like TRNGs or another sort of a way to address this, and there are already some like live implementations where keys are generated that are sort of inborn, generated within the hardware. Okay, so that's one problem we have to solve. Now we have this other problem of, okay, I get the hardware. Like some verifier now receives the hardware. You can't look at it with your eye and be like, oh, that looks good. You need some methodology for examining the hardware. And the most advanced, I would say, techniques have limitations. You have like scanning electron microscopes and focused ion beams, which sound like something from Star Wars, or these like kind of ways that you can image a chip, but typically they require you to destroy the chip, to like very finely delayer it and like take pictures through these layers. And that like kind of works. You can say, okay, I have this batch of chips, I'm going to randomly sample some of them and break them and investigate them, and so the manufacturer now is like taking risk, and like just the risk of being caught is enough to not do it. But ideally we don't have to break these chips. And then you have like non-destructive stuff. But right now, that like I think the foremost non-destructive technique is this like X-ray tachometry, which requires this like very, very large light source, like the size of like several large buildings, and it's just like it's not something you're going to run in your like local neighborhood. But there is some interesting stuff happening there with like infrared imaging, which is I mentioned in the article, and like Bunny, who's like a hardware icon, is working on. Then that imaging is one problem, generating the key is one problem. The other problem is like getting a reference. Like okay, so yes, I've generated an image of this chip, but now I need to compare that image to something which I can then trace back to some logic that I can audit, and so that logic needs to be open. But so like chip logic is like typically written, it's like either a set of gates, or it's like something that looks like code, like Verilog, and that isn't. You can't compare that to an image of a chip. And so we need something else. And we have a couple of ideas there, but just like open sourcing stuff is very hard in the hardware world. And so we can campaign to get more stuff open, and that's a whole other discussion, but there's some techniques around that. And then finally, we have this last problem of, I think I've covered all the problems.
So there were, I'm kind of cheating because I have it in front of me.
Oh, there we go.
There's the making verifiable designs, which is if chips have embedded keys, can we tell
Mm-hmm.
through inspection if these keys are trustworthy? So this is the puff and the
Right.
tamper evidentness, and the fact
Oh.
that if you tinker with the hardware, something changes.
Right.
Yes, I reminded you of something.
Yes, yeah, you've reminded me. So okay, so these are puzzle pieces, and if you're just trying to like make sure that your ledger works, this is enough, right? So if you're like very skeptical, you can receive your ledger, then take it to your local microscope or do it yourself, and use this infrared to image your chip, or assuming we've solved this problem, and then you compare it to the open source design. It looks good, and you can trace it back to the design, and you know that no one has a copy of this key. It all looks great. But if you're in this remote attestation setting where you don't have access to the hardware, there is an additional step which you need, which gives you assurances over this hardware. So if you're in the setting where you first custody the hardware, you give it a look, and then you ship it off to wherever it needs to go, that will provide you some assurances, assuming that it's like hard to break it once you've verified that it is complete and correct, which is a problem in and of itself. But in the case where the user can't physically custody the hardware, they need to be assured some other way. And so the problem there is to develop this kind of like verification protocol where you have some like distributed set of verifiers for like different geographies or whatever, different trust assumptions, and through some random allocations and whatnot, you examine these chips and you try to design this protocol so that even if some of the verifiers are malicious or some of the verifiers are being bribed, the system is still sort of robust, and the user knows that okay, this chip has gone through this verification process, and because of that, I have like relatively high confidence that it hasn't been tampered with and it's correctly implemented. Assuming 1/3, 2/3, or something like that is honest or they're rational or something like that. And so what you end up with at the end of the day is this like certificate generated from this trust minimized TEE, and the assumptions that the user has to make are like, okay, they're hardness assumptions. Like I assume that no one has extracted this like puff key or whatever other sort of hardware assumptions there are, but I think that's like one of the key ones. But the other is that this verification committee has done the right thing and is operating correctly. And of course, you can like commission additional verification, these kind of things. But really, what we've ended up in that world with is a world where we can like front load all these trust assumptions and have like this very distributed assessment, and then have this threshold honesty assumption or this whatever assumption you'd have over this committee, which is kind of what you'd have with MPC as well. But with MPC, we're not front loading it, and so we have all of this overhead of like interacting with the committee while we're doing the computation. And I guess it's like a bunch of other differences where the computation is known before the committee decides whether they're honest or not, whereas in the verification setting, they don't know what the chip's going to be used for, and so it's harder to do attacks. But that's kind of the big picture. A lot of words.
It's wild. How so many moving pieces. But this last part is basically you're saying that, okay, we have these tools for inspecting that the hardware and the supply chain that got the hardware where it needs to be is done correctly through the, oh man, I forget through the analysis, which some of it is destructive, some of it is non-destructive, through comparing this image to the reference. But to do these things, you need to have physical access to the hardware. So for the use case where a user is just trying to run some attested computation on a TEE, how do they trust that this TEE is kind of set up correctly? And here you're kind of conceptualizing this protocol that gets these other parties to go and verify that the hardware is good.
Yeah, that's it. I feel like it's not a rational move. If I was a strategic agent, I would say no, we cut it at the half hour. Like I've made my claims. And now, before anyone can ask any questions, like with time's up,
quit while you're on top.
Yeah, exactly.
So going back to one of the previous things you said, specifically around imaging the hardware and comparing it to what it was supposed to be. And you talked about this. You talked about this being difficult because this kind of like you're not able to make this transformation as easily because not all of these intermediate pieces are known or open or are open source.
Right.
So how does that, and what are the artifacts that are changing hands through this process from the chip maker to this end where, there's some verifier kind of like peeking into the hardware?
Okay, so I think the first thing to say is that the hardware, like design and manufacturing ecosystems, are very rich, and there's many different actors and lots of different people who own IP. So like I've done throughout this conversation, will probably skip over a lot of detail. But the idea is, the high level idea is, the designer starts some idea and they write this code out in like a Verilog. It's the logic of the chip is written in that code. And in doing this, they'll probably want to use some, components like a CPU or like really most parts of a chip. And they will license this from some other third-party provider. And this will come again in code form typically. And then they will synthesize this high-level logic, which we call the RTL. And the RTL will give us a netlist. And a netlist is just like a series of gates and or not whatever. And that describes like the logic of the chip. And, there's some massaging that happens there to get like the netlist that you want. And then this synthesis happens with private software that's provided by some other, vendors that license the stuff out. It's super expensive, it costs like millions of dollars to do it. And there are some open tools, but typically you have to use this like closed source stuff. Then the next step, which the designer is still doing, is they use this closed source software that we're using to get from like RTL to netlist to also then go from netlist to the actual thing that looks like a chip. It's like a picture of the chip, like a layered image of the chip called the GDS. And to do that, they need this closed source software that the EDA that they rely on, but they also need something that the fab provides, which is called a PDK, process design kit. And this will provide the necessary information so that when the chip designer provides their this GDS file to the fab, it has been set up in such a way that the process the fab uses to produce these chips is actually compatible with the design. Like it can actually execute this design. And so the important things to know here are that pretty much all of this stuff is closed source, because you're like licensing most of the time. If you want performance, security, and these kind of things, you're licensing these different components from some third parties, and the third parties, they make money from licensing their stuff. And I guess like the hardware will just has this like standard of being closed. So they require you not to open that design up. And this is like the position that Ledger's in, right? They don't design the hardware, but they ultimately suffer from these limitations. Then the GDS requires a PDK, right? And which is provided by the fab. And this PDK is given to you under NDA. So it's not even just like copyright issues. It's like, it's an additional legal agreement. And so that like is much harder to open up. On the fab side, the important stuff to know is that the fabs have different process nodes that they use. So all technology are these like big number process nodes. So that you'll have like 130 nanometer, 180 nanometer. This kind of stuff is open. Like that PDK is open. There's no NDA necessarily there, but only a couple of fabs do that. And that technology is just like slower, and less space efficient, less cost efficient than the cutting edge stuff. The cutting edge stuff is like 2 nanometers, which like TSMC does. And for that kind of stuff, the PDK is definitely closed. So I guess I'm vomiting information at you, but that's kind of the structure, right? And so what some of these companies do, you have in the last couple of years, you had a couple of projects, I should say. Some of them are not necessarily companies, that have tried to open up as much of their chip as possible while keeping some performance. So OpenTitan is an example of this. Tropic Square has been working on it, but they haven't opened up anything yet, but they plan to, I believe. And what they've done is they said, okay, look, some of this high-level logic, some of the RTL, this we can open up. Because there's some open source components, we'll do some in-house. But we can't do all of it because really, like, we just like doing the RISC-V core on our own, or doing this, whatever component, DRAM interface or something, that's like too hard. And so we'll just license that, and that part of the RTL will keep closed. But then when it gets to the GDS, which requires a PDK, we're not even going to try. That's like we can't do 130 nanometers because we need to be performant, and so we're going to do it on some lower process node and just keep the GDS closed. And so from our perspective, in this effort to get this trust minimized TEE, there are two high-level approaches. We could just campaign to like march down the process nodes and get stuff open. And I think we actually can do, like, there's a good reason to believe we can do this, because already these like open fabs are busy open sourcing on these process nodes. And there are a lot of process nodes between what is open today. I think like Skywater announced 90 nanometers, and what the state of the art is. That is old technology, and they can actually make more of that open. And there are people in this open source community working on open PDKs and these kind of things. So if we can show the value of trustless hardware, and we can, show this, especially if we can do it to governments, then we can maybe succeed in that direction. But assuming that's hard or it takes a long time, and we just have to assume that like the GDSs are going to be closed, what else can we do? Well, there are a couple of other ideas, but the main idea is like, look, we have this technology, the ZK, we have like SNARKs, we have trusted hardware, which is an interesting idea, but which also provides these kind of privacy guarantees. And so we can, without exposing the GDS, without exposing this file, which we're not allowed to expose, prove that an open high-level logical description like a netlist and an image of the chip actually match to each other, either using the GDS in the background to compute this proof, or maybe using some other like smart algorithm. And so both of these, I think we should pursue in parallel. And because we have both of these, it feels like we should be able to get something working not that far into the future. Yes, many words again.
That all makes sense. It's wild that the simple intermediary solution is going to rely on us making a snark of this large PDK program.
Well, I guess I should say there's actually the third approach, which is just to say, look, we're not going to open source any of this stuff. You don't have to audit it at home. We're just going to get we're going to get some trusted set of verifiers. We all nominate some universities or whatever, and these guys will be given the GDS. And they'll sign an NDA, and they promise not to reveal it publicly, but they will look at the chips and cross-compare the images and just attest to the blockchain, true or false, this thing looks good. And that's probably not ideal, because we probably are limited in the set of verifiers we can use. You can't verify at home, but it is certainly an improvement over what we have today.
Yeah, this all makes sense. Yeah, so kind of zooming back out, we've talked about why to try to bring this gargantuan discussion to a synthesis. So we've talked about why TEEs are an important primitive, and the kind of use cases they have both in the blockchain ecosystem but also outside of it. And we've been talking through the three main threat vectors that, when you kind of think about this from first principles, these are the places that something may go wrong, right? There's a software adversary, there's a physical like hardware adversary, and there's a supply chain adversary. And you've kind of very systematically mapped out the different approaches we can take to harden this whole stack. So I guess one of my closing questions is, where do you think we are in the longer arc of building this trustless TEE?
I think probably infinitely far away from the ideal. But I think that there are some interesting milestones that we can hit in the next couple of years that should provide the proof that this is an interesting and valuable direction, and ideally cascade a larger move and get people behind it.
Yeah.
So I mean, maybe just to give you like some social context on this, there are, like I was mentioning, this like hardware team in Belgium. There are other hardware teams in crypto that are like actively exploring doing something in this direction. Like, can they have something that's remote attestation that is has all the necessary parts of the RTL open at least? There are definitely some smaller things we can do where maybe we don't have this fully fledged high performance TE, but it's it can do a couple of specific use cases that we care about. So I think that the social energy is there. There are people who are interested in funding this research, who want to have trustless TEs. There are people who are capable of doing this research and like implementing this stuff. And really, like what we need to do now is like harness this energy, and that's what I'm working on.
Right. And so maybe kind of closing with a call to action. Who are the folks that what can people kind of get involved with? Where do you think people can help?
If you know anything about hardware security, that would be great. You should speak to me. If you're a hardware person in crypto, or a hardware person who cares about open hardware, about minimizing the trust assumptions, we do need your help. There are very many like sub problems, and your skill set's probably helpful for some of them. If you are in the crypto sphere and you care about minimizing trust assumptions and reducing the centralization of power in the world, then this is something you should care about. You should tell people about it, spread the word. And if you're controlling lots of funds, also speak to me. There's a lot we can do, and there's no reason. If it isn't the group of people who listen to this podcast, I don't know who's going to do it. So that's the message. Yeah.
Right. Yeah, it's a horizontal effort across the board, right? There's like academics, there's infrastructure, software, there's all sorts of things that are involved in moving this forward. And I mean, I, for one, reading through some of the recent material you wrote, just got a sense of like, you guys, there is a mountain of work to do, but I get the sense that you're on top of it. So I feel good knowing that someone like you's driving the charge here.
I will not challenge that. Thank you.
Well, thanks so much for taking the time, man. This has been really great.
Thanks for having me. Thanks for letting me get the message out. Hopefully people hear it.
Hey, I have a small ask here. If you've been listening to these conversations and want to support what we're doing here, I would really appreciate if you leave a rating and a review for the podcast. It might seem like a small thing, but it actually makes a big difference to help other people discover the show also. Thank you, and I'll see you again soon.